Systemy rurowe w branży morskiej, to jest na przykładzie branży morskiej, bo systemy rurowe znajdują się generalnie w każdej branży, więc tutaj czasami łatwiej w obliczu danego przemysłu omówić, jakie systemy jesteśmy w stanie tutaj zasymulować, przewidzieć i na przykładzie branży morskiej systemy balastowe, systemy osuszania, czyli zbierania jakiejś wody zełzowej, systemy grzania, chłodzenia, systemy sprężonego powietrza, wody słodkiej, morskiej, systemy przeciwpożarowe, systemy tak zwanego komfortu, czyli ogrzewania, wentylacja, klimatyzacja, smarowania, wspomagające napęd, chłodzenia elektroniki i wiele innych. Zrozumienie tych systemów i dokładna symulacja ich jest kluczowa dla optymalizacji i wydajności naszych systemów, efektywności energetycznej, optymalizacji i kontroli procesów, do innowacyjności, no i przede wszystkim dla bezpieczeństwa. Możemy tutaj zapobiegać potencjalnym katastrofalnym awariom, takim jak przecieki, pęknięcia, przegrzania. Co to jest system Simcenter Flomaster? To oprogramowanie do symulacji 1D systemów cieplno-przepływowych o dowolnej wielkości i złożoności. Kluczowe cechy i korzyści to jest umożliwienie inżynierom tworzenie cyfrowego bliźniaka systemów termoprzepływowych, tak naprawdę takich systemów rurowych, gdzie złożoność takich systemów do obliczeń, jeżeli tradycyjnymi metodami byśmy chcieli to policzyć, jest to nieopłacalne z punktu widzenia czasu tak naprawdę, natomiast takie systemy 1D systemowo potrafią nam przeanalizować i dać odpowiedź, jak dany rurociąg jest zaprojektowany. Pomaga podejmować świadome decyzje projektowe na wczesnych etapach procesu, czy dane średnice są odpowiednio dobrane, czy są dobrane odpowiednio przekroje poszczególnych rur, wymienników itd. Redukuje to ryzyko awarii, obniża koszty oraz czas wprowadzenia produktu na rynek. Gdzie możemy takie systemy 1D za pomocą Simcenter Flomaster zastosować? To są różnego rodzaju systemy dostarczania gazu, scenariusze związane z pompami, równoważenie przepływów, systemy przeciwpożarowe, zraszające, dobór wielkości systemu, dobór rozmiaru rur, pomp, zaworów, napełnianie systemu również ze zbiorników otwartych, analiza scenariuszy, co jeśli zawór będzie otwarty, zamknięty, rozruch i testowanie systemów, czyli tak zwane, możemy też symulować uderzenia hydrauliczne, czyli gdzieś tam zawór jest otwarty i jak tam na początku się będzie zachowywał systemy chłodzenia, dystrybucji, analiza tłumienia przepięć. Jak wygląda schemat projektowania i symulacji? Można podzielić go na takie 4 etapy. Szybkie tworzenie modelu, efektywne dopasowanie i równoważenie systemów, symulacja oraz współpraca symulacyjna z innym zewnętrznym oprogramowaniem. No więc najpierw musimy zbudować model. Najczęściej i tak modele są budowane w ramach projektów, czyli mamy już takie rurociągi zdefiniowane w systemach cadowskich. Tutaj przedstawię proces uzyskania takiej geometrii 3D, przeniesienie jej do Simcenter Flomaster. Jak to wygląda na przykładzie NX z modułem NX Routing, gdzie inżynier nie musi tracić czasu na budowę takiego modelu po prostu do symulacji, tylko już gotowy projekt, skoro został zdefiniowany, to możemy go sobie przerzucić. To oczywiście tutaj jest na przykładzie NX-a, natomiast czy ktoś używa Solidera czy innego systemu, też są narzędzia, które pozwalają taki model przenieść. I tu króciutko właśnie będzie pokazane przeniesienie modelu z NX Routing do Flomaster.
With all of the piping design done with NX routing, why recreate the system for 1D simulation? Piping systems created using NX mechanical routing can be exported to Simcenter Flomaster using the piping component file. The 3D model can then be imported into Simcenter Flomaster.
Napisałam, że nie, że Ula jest królową podpić, że jej przekaże, żeby się z nim skontaktował. Chyba 3 tygodnie minęły, ona się nie skontaktowała. To pytałam Maćka, no nic nie wiem. No to kurwa nie napisałaś mu przez te 3 tygodnie? No nie. I ja mówię, no to mu napisz. Ona okej. I ja
Take seconds instead of hours or even days. Connections are automatically made and all geometric data is added. With a few steps, the system is ready for analysis, saving up to 90% of the time needed to create the model.
Jak było widać, w kilku krokach możemy model 3D przenieść do Flomaster. Mamy parametry rurociągów, mamy parametry poszczególnych komponentów. Oczywiście po wczytaniu możemy też odpowiednio sobie dobrać kolejne parametry. I to jest właśnie kolejny krok, że po utworzeniu nadchodzi czas na dobieranie komponentów, ich parametrów w celu uzyskania najlepszego możliwego projektu. Simcenter Flomaster oferuje szybki, niezawodny solver, który umożliwia przeprowadzenie tej operacji szybko. Wystarczy przyciągnąć komponent z biblioteki i połączyć go z innymi elementami. Po zaznaczeniu komponentów możemy szybko wprowadzić albo parametry, albo wybrać specyfikację, która jest zapisana w bibliotece. Następnie proces obliczeniowy, gdzie każdy element jest liczony, na każdym komponencie jesteśmy w stanie sczytać wyniki, co się dzieje. Wizualnie też nam ładnie kolorami podpowie informacyjnie, co się dzieje. Mamy też analizy zmienne w czasie, więc wynik na histogramie też będziemy mieli widoczny, jak na przykład się ciśnienia czy prędkości zmieniają. W ten sposób możemy wiele scenariuszy analizować i dzięki temu szybko możemy dobrać odpowiednie komponenty i zredukować koszty operacyjne na jakieś testy. W kolejnym etapie to jest co-simulation, czyli współpraca z zewnętrznymi oprogramowaniami. Simcenter Flomaster oferuje szeroką łączność z innymi narzędziami z oferty Siemens, ale również spoza niej. Więc możemy sobie taki model przepływu przygotować. Jeżeli mamy model przepływowy policzony we Flomaster, mamy wyniki z analizy dynamicznej w stanie nieustalonym, czyli zmienne w czasie i taki wynik ciśnień w poszczególnych komponentach możemy przerzucić do systemu zewnętrznego, żeby policzyć wytrzymałość rur ze względu na ciśnienia. No i tutaj też króciutko filmik pokażę, w jaki sposób możemy tutaj przedstawić. Czyli mamy jakiś element gdzieś możemy tutaj na danym wynik po prostu wynik sygnału po prostu na danym zaworze, jak on wygląda. Następnie w poszczególnych komponentach mamy wyniki funkcji czasu, czy tutaj na jakimś kolanku też mamy wynik funkcji czasu. Tutaj na rurze też mamy histogram, jak wygląda ciśnienie. Następnie za pomocą import-export możemy wyeksportować ciśnienia hydrodynamiczne. Wybieramy sobie format, do jakiego formatu chcemy to wyeksportować, które wyniki, z których komponentów. Jeżeli chcemy wszystkie, wystarczy zaznaczyć i kliknąć eksport i mamy poszczególne wyniki już wyeksportowane. I mamy tutaj, jak widać, w funkcji czasu po prostu tabelarycznie wyniki pokazane. Więc też parę kliknięć i wynik przetworzony. Podczas budowy projektu też możemy przeciągnąć poszczególne komponenty i je zbudować. Flomaster posiada bardzo rozbudowaną bibliotekę, szeroką bibliotekę, jeżeli chodzi o budowę właśnie systemów rurowych, ale i nie tylko, takie jak zawory, układy dwufazowe, zbiorniki, generatory mocy, rurociągi, wymienniki ciepła, komponentów do systemów zasilania w powietrze, jak dysze czy rozdzielniki, sterowniki, kolanka, przejściówki, jakieś pompy, przepusty, źródła zasilania cieczy czy gazów o stałym, jak i o zmiennym natężeniu przepływów, wentylatory, sprężarki, elementy reprezentujące stratę energii, takie jak opory miejscowe czy tłumiki itd. Oczywiście kategorie też są rozbudowane, czyli zawory mamy zwrotne, regulacyjne, bezpieczeństwa, ograniczające przepływy, separatory faz, skraplacze, parowniki, komponenty do wymiany układów, zbiorniki otwarte, zamknięte ze zmienną pojemnością, zbiorniki w układzie ciśnieniowym, turbiny gazowe, parowe, generatorowe energii, rurociągi proste, rurociągi ze zmienną średnicą, wymienniki ciepła, wymiennik płytkowy, rurowy, radiatory, spiralny wymiennik ciepła, chłodnice. Jeżeli chodzi o układy powietrzne, to dysze powietrzne, rozdzielacze powietrza, sterowniki, regulatory ciśnień, regulatory przepływów itd. Także to możemy sobie dokładnie zasymulować cały układ procesowy. Natomiast szereg komponentów zawiera już predefiniowane dane, czyli dane odnośnie strat ciśnień na przykład. No i tutaj na przykładzie trójnika, czy to będzie trójnik T, czy trójnik Y, jesteśmy w stanie tutaj zmapować po prostu, jak dany element się zachowuje. Oczywiście też na przykładzie gdzieś tam danych elementów możemy sobie określić, jak on będzie wyglądał, więc w przypadku Flomaster standardowych komponentów automatycznie wprowadza odpowiednie wartości strat ciśnień lub energii, które odpowiadają rzeczywistym warunkom operacyjnym, więc nie trzeba tutaj każdego elementu gdzieś tam walidować, tylko po prostu mamy tą bibliotekę. Dzięki temu korzyść z użycia danych empirycznych zwiększa dokładność symulacji, uwzględnia rzeczywiste dane zapewniające bardziej precyzyjne wyniki symulacji, które lepiej odzwierciedlają działanie systemu, no i skraca to konfigurację całego układu dzięki właśnie gotowym elementom z empirycznymi danymi. Jak wygląda taki proces pracy w naszym układzie? To jest po prostu stworzenie projektu, czyli jako krok pierwszy to jest stworzenie projektu, następnie stworzenie danego układu przepływowego, budowa modelu, przeciąganie poszczególnych komponentów, łączenie je ze sobą. Przypominam, że większość układu od razu nam się przeniesie z modeli 3D. Następnie ustawienie poszczególnych komponentów, czyli tu mamy jakąś pompę, mamy jakieś moc pompy, jakieś prędkości obrotowe, przepływy to możemy sobie tam też dodatkowo poustawiać. Następnie włączamy symulację, no i analizujemy wyniki. Jeżeli chodzi o analizę wyniki, to czy wynik będziemy mieli widoczny od razu tutaj przy poszczególnych komponentach, czy jakieś zewnętrzne wykresy niedane, to jesteśmy w stanie tutaj w prosty sposób uzyskać. Flomaster umożliwia obliczenia ze względów na 3 typy płynów: nieściśliwe, ściśliwe, dwufazowe. No i w zależności od danego typu płynu, który chcemy zastosować, mamy poszczególne rodzaje analiz, które jesteśmy w stanie tutaj uwzględnić.
So in the next few minutes, I will cover the following topics that you see in the agenda. So starting with the application example on marine cooling systems, we'll be looking at how you can size pump, sizing heat exchanger, and also looking at pump failure scenarios. This will be followed by a demonstration of Simcenter Flomaster software itself. So there'll be a longer, full demonstration of how to build a simple model, analyze it, well, input data, and then analyzing. And then we will be looking at some briefly customer success stories. And those stories are from a number of our customers, including BAE Systems Submarines in the UK, Hyundai shipping industry in Korea, and Japan Gas Company. And then we will conclude and take any questions if you may have. Okay, so with that, we'll look at how you can model marine cooling systems in Flomaster. So we all know marine cooling systems is an important system within a vessel which provide efficient and centralized cooling for various onboard machinery and systems on ships, systems relating to engine, generators, HVAC, and also air compressors. So you have a number of systems are being cooled through the central cooling system, which makes it a very important system for any ships. Generally, the engineers tend to look at problems when it comes to central cooling systems, how to size the pump or the pump to meet system requirements. They also look at things like sizing heat exchangers, also pump failure scenarios. If you had more than one pumps, what happens if you suddenly have one of them shuts down or have a abrupt failure due to any technical issues and so on. And then you're looking at well, if those kind of things were to happen, then you will end up having pressure surge, and how can you install surge suppression system that will alleviate excess pressure from the system to make sure the system will still continue to run in the right way. You've seen examples on component sheets that Michael has shown earlier on. Flomaster comes with a catalog of components that are pre-coded, so a user who's using Flomaster will only have to drag and drop to build a full system. And then once the schematic is done, then you look into adding the data, and even for every single component, the data sheet is color coded so what that means is you would know immediately which are the mandatory data field and which are the optional, and so on and so on. So it's very easy to use the software itself. So to build such a system, the diagram that you see on the left on the screen is a typical central cooling systems that you find on ships. This one is taken from a company website, and And then all the components that are required to build such a system are already in our catalog, as Michael has shown you. Things like heat exchangers, pump, pipes, junction, valves, and so on and so on. So I'll go to the next slide. So what you see on the screen here, on the left-hand side, is a pre-built model using standard Flomaster components. So the system is built with heat exchangers, pipes, and they are labeled so you can see it. There's also a pump component that we see here. So essentially, you have seawater circuit, and then you have the freshwater circuit on the right-hand side, right, where things are being cooled. And then you have the central cooler heat exchanger on the left-hand side of the model. So all those components are inbuilt and available on the catalog. So it's very easy to build. But to look at how you would size the pump, so if you went to a component, the pump component data sheet, so you would see what you see on the screen on the right-hand side. You would have to enter like rated flow, rated head, speed, and so on. Most of these data, you can find them or are available on pump manufacturers' performance data sheet. So if you were to get performance data sheet from pump manufacturer or whoever is supplying the pumps, they will send you a performance map, and in there all those data can be found, right? So those data can be easily put into the data sheet. You would also have to enter pump performance curve, and that's what you see. And this is what the suppliers generally provide, so that quite easily to enter into the system. Once you have input all the data for various components, you can run the model in steady state or transient, and then you will be able to, if you were to run the model in steady state, then you can plot the data on the schematic as you see on the right-hand side. So you can plot temperature, pressure, flow rate, Reynolds number, whatever, anything that is available, power efficiency, and so on. All those things can be plotted onto the schematic, so you can immediately see get an upshot of the system performance on the model, and those data can be easily imported into report for your sharing with your customer. On the left hand side, you see you can also plot a system curve against the pump performance, right? So if you run this system in transient, you will be able to see where the pump is operating at. So that gives you your flow rate, head rate, efficiency, and power, and so on and so on. Yeah. So you can test different pumps quite easily using different pump setting. So what you see here, if it doesn't meet, if you don't get the right efficiency, then you can change you can change performance setting. You can simply increase the different parameters, perhaps changing the speed of the pump, or or any other things that can be changed on the data form. Then, if we're to look at how do you model or size heat exchangers? So again, on the left-hand side of the diagram, you can see the cooling circuit of the model, right? And then the red square that we have, it's indicating you a heat exchanger model from Flomaster. So again, there are a number of ways you can model heat exchangers in Flomaster, depending on the level of data that you have. If you simply have heat duty, for example, or the Q, or the heat flow rate, you can enter that, and then Flomaster would calculate the transfer of heat, or the inlet-outlet temperature, flow rate, and so on. So it will calculate all what you see essentially on the right-hand side. So it enables you to calculate or predict the performance, efficiency, and thermal performance of a model. So I mentioned there are a number of ways that you can model heat exchangers. So what you see on this slide are a number of heat exchanger types that are available on Flomaster catalog. So these are like your standard heat exchangers, cross-flow heat exchangers. You have advanced heat exchanger, shell and tube, plate, and so on. So there are, obviously, a whole range of heat exchangers that are available. Generally, what we generally tend to see is the first column that you see, the standard heat exchangers are being readily used on a day-to-day basis. There are two ways of two levels of complexity you can model. One with, depending on if you're geometrical data, and the second is empirical information. So I'll give you a quick example of a geometrical data. So starting with on this slide that you can see, we have U-flow heat exchanger that's been modeled in Flomaster, and the arrow pointing you to the data form. So here, as you can see, in the model type is set as geometric, and then you can set the material type of the heat exchanger. You can then set the tube data, as you see, how many tubes, for example, what shape they are, what length they are. So these are the geometrical based information. So you can enter that. Assuming that you have that, then obviously you can do that. If you have the fin and lower data of your heat exchanger, that can also be input in here, as you can see if you follow through the arrow. And then the step before the results is where you can show the configuration of the heat exchanger or the tube configuration. So if you have flow coming in, as you can relate to the diagram on the top left, so coolant flow coming in, and then it kind of goes into U shape, and then going out at the bottom, coolant flow output. So you can kind of configure that on the wizard. And then when you run the model in steady state, for example, you can see the results, which are the left bottom diagram. So you can plot the velocity results, temperature, performance results, which is an important part of it, and then the flow density results as well. There are also other things you can plot, like Reynolds number, heat flow rate, and so on. So that's your quick snapshot of geometrical. Now going to the next level, empirical data. So this is based on, again, the performance data that you may have. So there are, again, you would need to enter pipe area 1 and 2, and then this is shown in the figure or the diagram on the top right-hand side. And then depending on what level of data you may have. So you may have just thermal duty, for example, as I mentioned earlier. Yeah, you will be able to run the model in steady state or transient. So the red color and data entry points are the mandatory data fields. So you've got to enter those to be able to run the model. Anything else is optional, depending on what data you may have available. You will get your output based on that. So having a thermal duty, you will be able to run the model and get temperature, result, output, input and output, and so on. So there are different types. You can study we will share the content later on, so you can study the actual, what data or the full data list later on. So in terms of, so assuming you've entered data, you run the model in steady state. Here you can see on the right-hand side the full list of results that you could predict using Flomaster. So you can see the kind of information you will get: flow rate, mass flow rate, velocity, total fluid flow, almost everything that you would need in terms of predicting the performance. Arm 1 and 2. So if you look at what these means, is basically the input to. One is signified as the input of the flow to the heat exchanger. Output is number 2, and then if you have the heat exchanger, you will have 4 2 inlets and 2 outlets. So again, you will have arm 3 as an inlet, and then arm 4 as outlet, which is why you see arm 1 and 2 and 3 and so on. So that just to explain you what that means. If you were to make comparison to the simulation. Sorry, I think I missed a slider here. So back on the heat exchanger, if you were to then perform parametric studies on varying different parameters. So in this case, for example, you try to size a heat exchanger. You can you can enter different length of tube or number of tubes, and then you'll be able to run the model in steady state or transient and understand the compare the result, temperature results at the outlet. Obviously, it's going to vary. If you were to have a more number of tubes, you would expect the outlet temperature to be lower than what coming in, and that's what is reflected in here. So you'll be able to generate such result output, and then that can be shared with the client and so on. If I then go to the seawater pump trip, so seawater circuit cooling pump, I mean, obviously you can predict failures. There are a number of ways you can do that. I mean, generally people tend to ask such question is, if we had pumps and if one or two of them failed, what would happen? I mean, how long would it take for the system to overheat? Any primary utility inlet temperature above certain temperature fill, for example, in this case is written as 85. You may want to see what would happen if it was to go, when would it go beyond 115 or 20 or whatever the the temperature range that you may want to avoid. So those things can be modeled in Flomaster as well. So again, if you pump is the focus in this case, so we'll be focusing on seawater pump. Again, what you see here on the left hand side is the data field for the pump component. What is important to simulate pump failure scenarios is the pump inertia and motor inertia. So when you switch off a pump, so you would set the logic states. So initially running at a constant speed, and you want, let's say, at 5 second motor to shut off or trip. So what will happen? The pump will run, based on its inertia until it comes to rest. But so what you then interested in to analyze is what will be the the pressure rise, for example, as a result of that. What will be the temperature rise as a result of that, and so on. And this is what is what you would set that, and it's very easy to set in the component itself. Once you have set the data, you can run the model in Flomaster in transient form, and then you can simulate the rotational speed of the pump. The pump will quickly, over a few seconds, based on its inertia, come to rest, and as a result, you will start to see the temperature rise in different heat exchanger components. Because when you start to lose capacity, in this case we only have one pump, so if you lose the pump which is supplying the coolant or fresh water cooling in the circuit, then obviously it's just a matter of time we will start to see temperature exceeding the range that we set, perhaps 115 or 20. So you can then estimate how long it will take for a total failure. So in this case, it's showing us it will take just over 4 minutes to be able to have a complete failure. So it gets to show how you can do pump trip. You can, by default, the pump runs at a constant speed, right? But you can perform predict scenarios of pump failure. This is important especially for battleships, but also for cruise ships, where well, I suppose it can be relevant for any kind of form of ships, where you want to analyze, if you have multiple pumps, what would happen if half of the capacity was taken out because of pump failure. I mean, the vane can fail and many things can happen. So that just go to show you what sort of thing you can do to analyze within Flomaster. So with that, I will we have a demonstration video here. We will run through this, and then hopefully you get a full view of how how you can build a simple model from the beginning, analyze steady state, transient, and then view the results on the schematic and so on. So
this is just going to be a really quick overview, just to kind of give you an idea of what the software looks like and what it can do. So this is what Flomaster looks like. We do have something called the launch pad, where we can, for example, pull in some sample systems. And importantly, if you wanted to do this 1D, 3D cosim with FlowBFD, we can import equations of performance from other 3D tools as well. But really what I wanted to do was just show you how to build a very simple model. Okay, so for example, let's create a flow source. Okay, so over here we have the Flomaster catalogs, and it really is just a drag and drop functionality. So over here, let's say I'm going to have a flow rate of, let's say 100 gallons per minute into our system. Okay, and the most basic component in a Flomaster network is a pipe. Okay, so here's a pipe. So I'm just going to drag a pipe in. A pipe, we need to give some information about this pipe. So for example, let's say it's going to be a 100-foot pipe. The diameter is going to be, let's say 4 inches. And then less intuitively, we do need to give some internal friction information, so things like a roughness. So I'm just going to give a very low roughness, and that's going to drive what the pressure loss through this particular component in the Flomaster network is going to be. Okay, so next I'm going to pull in a valve. Okay, a valve, simple ball valve. This is going to be controlling our flow. Now this is really really important. For components like valves, T's, pumps, a lot of common components, a lot of the performance data for this valve is incorporated into Flomaster. Now this is kind of, the very common components that's actually pretty tedious to find information on the performance. So if it's actually built in, this is a huge time saver. And this has the valve position versus the loss coefficient. So as we open the valve more, it becomes less restrictive, and there's going to be less of a flow resistance across this valve. And this valve will actually scale based on the diameter. So a lot of components have that performance data actually built in, which is a really big time saver. So let's say it's going to be 80% open, and I'm just going to be looking at an incompressible steady state solution. So that looks good. I'm going to create a copy of my pipe over here, and then let's say it's going to be this time this section of pipe is going to be 500 foot, for example. And then finally, I need to give an outlet boundary condition. So let's just pull in a pressure source, and that's just going to be atmospheric pressure. And then now the fun part, we can just start stringing things together, right? So I've pulled in my components, need to connect these guys all together like this. And this is about as simple as a Flomaster network can get. Okay, so over here in the simulation data, we choose our simulation type. This is going to be an incompressible steady state analysis. If I look at things like the default, the ambient conditions, so I can see temperatures, pressures, and gravity. I can choose under my materials, look, my liquid type is water, but I can just as easily click select item, and I could choose like crude oil or Jet A1 gas fuel, aviation fuel. Mineral water. So there's all sorts of different fluids that you can either select from the library, or we can even create custom fluids from the NIST database. So it'll actually call out to the internet and create custom fluids with various blends in there of different liquids or gases, and it will create a material for you. Okay, so let's just click run on a simple model like that. And for a steady state, it pretty much runs instantaneously, right? Look, it's concluded already. I can click on the node, for example, and go to the results. And if I look at the pressure, I can plot that on the system, and you can see there's my pressure variant across my system. Let's undo that and look at the pipe, for example, and let's say I want to understand what the pressure loss on a certain component is. I can plot that on the screen as well, so you can see on my various components what the pressure loss in a specific part is going to be. Okay, so let's say that I wanted to now make a change, and rather than make it 80% open, I'm going to make this say 20% open, and let's run that again. So pretty much, again, instantaneous result. But if we look at the difference now, let's go to the result and go to the pressure loss now. And plot that on the screen, right? So we can now see a much larger pressure loss across that valve because it's a lot more closed. So this is just an example of the steady state capabilities of Flomaster. Now, if you wanted to do a bit more in the way of transients, which is really where the power of Flomaster is, then we can look at things like water hammer. Okay, so what we have here is the valve slamming shut, and then because it's I think it's an 8-inch pipe with water flowing through it, you get this hammering effect. This is the pressure pulse just banging up and down in this pipe. Very, very destructive. If you see, the pressure peaks at 21 bar, that's huge. That's 21 atmospheres, really, really destructive to piping network systems and something you want to avoid at all costs, okay? Just slamming close the valve like that, all that momentum hitting up against that valve is going to be very, very destructive. So what can we do to mitigate that, okay? So we can do things like close the valve a little slower, right? So that just stops the peak of the water hammer reaching all the way up to that height. You can see that we got a much lower peak now when we close that valve slower rather than slamming it shut. So, but we can see that the frequency of the water hammer is actually pretty much the same. So what we can do further to mitigate that is add, for example, like an air vessel, an accumulator, right? Air is compressible. It can take the sting out of that water hammer. So let's just put this on the first window and just run this again. And then we can compare different networks, understand what change that's going to have on the system as a whole, and quantify exactly what sort of damage or exactly what sort of peak pressures that we're going to be getting within the system with Flomaster. Okay.
Okay, so that's the end of the demonstration of Flomaster. It's a simple model been used to demonstrate to you how you can easily build any model from using the components from our catalog straight into the schematic, and then connecting them, and then go to each component to add the data before running the model to predict the output. So everything is done in one graphical user interface, or GUI. What that means is it's a very easy tool to use. Once you've learned how to use it, you can pick it up at any point, and you'll be able to walk through building the model. So it's a simple model that's been demonstrated, but you can build any level of complexity. I mean, there isn't any restriction to how many components you can have in a model. So it can be anything from 3 components to hundreds to thousands of components, and you can quite easily perform steady state, transient, etc., to analyze flow, pressure, pressure drop, velocity, and so on. Yeah. So I hope that given you a quick walkthrough of the entire workflow. I know my colleague earlier on mentioned, Michael mentioned earlier on, he can also import 3D CAD model from NX or any CAD packages that you may use, Aviva, Intergraph, and so on. You can import PCF data and be able to build the full-scale model in 1D, anything from minutes to within a day, depending on the level of complexity you may have on the model. So, yeah, we also mentioned earlier on that you can also, once you have run a simulation, you can export hydrodynamics force data into stress packages like CESA or CAE pipe and so on for other simulation. So with that, I'm going to go to my next topic, customer success stories. I simply want to take a few minutes to just give you a quick brief of some of our customers, how they're using our solution of Flomaster. So BAE Systems Submarines is a company based in the UK. You may have heard of them. They are one of the biggest defense companies in the world, and they develop many things. This particular division of BAE Systems, they focus on developing submarines only. All of nuclear submarine fleets of UK are designed by them. Now, they have been using Flomaster software for as long as I remember. I've been in the industry for 27 years now, and I've trained many of their engineers back in the early days, well over 20 years ago. They've been using Flomaster throughout all this time. They continue to use Flomaster along with our other solution from Simcenter portfolio, right? And they use Flomaster for piping systems. One of their engineers mentioned to me that in terms of the length of pipeline they have in a nuclear submarine consists of almost 50 kilometers length of pipeline. Now, all of that are done modeled in Flomaster, and you can see the scale that you can model, and then just telling you the length of time they've been using. It just gets to show the credibility of the solution that we have, and they use it on a regular basis to analyze systems of anything to do with fluids. So and I think the list that Michael presented you earlier, ballast system, cooling, sizing pumps, heat exchangers, so on, there is a huge list, and it's all done using Flomaster. Now, going to the next one, Hyundai Heavy Shipping Industries. Again, they are one of our longer serving customers. They've been using, again, for well over 10 years. So they use Flomaster for seawater system modeling, right? So they look at, again, understanding system behavior is a crucial part of the analysis that they need to do to be able to ensure that the vessel will perform as is best efficiency, and make sure it will last longer as well, because a lot depends on various systems, depends on the heat that's extracted by the central cooling systems and so on. So it's a crucial part of their design process. Hence, Flomaster is heavily used. In this particular case, it mentioned about the, analyzing maximum pressure due to pump failures. These are the kind of things are analyzed to ensure that in the event something goes wrong, the vessel can still survive and not going to have major problems that could cause a spill. The next example, Japan Gas Company. Again, so what they do here is, as you have, big tankers, they come into shore, they transfer LNGs, or in some cases that you have the crude companies or vessels that are coming to shore, and they transfer their material onto storage tanks. And what is important here is to ensure that you can do that safely, right? And you can do that within the time scale that you have to be able to unload, and then the vessel then goes into do other things. So all of those kind of things are simulated here. And they've been using for a long time as well. And according to JGC, they build their models automatically from CAD packages to ensure that they could have the speed, so they can spend more time analyzing their systems. Next example I want to briefly give this salt ship design, and it just gives you an idea. If you look into the picture on the left, top left, obviously there are lots of pipes or piping systems are within a vessel. There are lots of them. If you want to analyze particular, then obviously being able to import the data straight into system simulation package actually saves you enormous amount of time. And the reason being, each component carries length, friction data. You have the elevation data, which is equally important. If you get the elevation data incorrect in the model, or if you enter by human error, then you will get your pressure drop wrong. And if you get a pressure drop wrong, then the system curve will be wrong. So you can see how many things depends on every single data that we enter. So being able to import data automatically, first of all, it gives you that speed to be able to build the model, but it's also increases the level of accuracy that that it brings. And obviously, if you can spend more time analyzing it, this is where the real engineering works, that actually brings value to your company, to the work that you do, or to the engineer as well, because they can spend more time ensuring that they can design a better system. Yeah. So in conclusion, what you've heard today, Flomaster is a 1D system simulation tool. It has been in the market for well over 30 years now. It's originated from a company called British Hydraulic Research in the UK. And it comes with the software itself comes with hundreds of components that are pre-built, have been used over the last 3 decades. That the solution is very easy to use. You simply go to catalog, drag and drop components. Almost everything that goes into designing or into vessel piping system, you will find them in the Flomaster catalog. So you wouldn't have to really create anything from scratch. 99.9% of them are available. If there's anything required building, you can import 3D CAD. That can be then simulated into 3D environment and then imported into Flomaster. But that's a rare case. Most components are available within the catalog itself, does the job as it does for BAE Systems and other companies that I've shown you earlier. It comes with one GUI that you get to do everything there in one environment. There is no pre-post packages that involve everything in one environment. In terms of data, as I said earlier on, it's all color-coded, so you know exactly what you need to enter. All right. Again, it helps you to drive the process to ensure that you can run the model. And once you run the model, you can output the results and plot them into schematics. So all the results are there. You can visualize them in terms of flow rate, pressure, density, flow, mass flow rate, and so on. You can also plot them in color-coded form. So as well, I mean, that's fantastic for reporting, especially for large vessels. You can also perform, as you've seen in the demo, transient simulation. And during the simulation, you can also view the results on chart form. So you can see if you were to have a flow varying because of valve closure, whatever, those things can be visible on the as you run the software. And then you will be able to generate a full report as well. That can be part of your full fluid report.